So what I want to tell you about today, without further ado, is intense laser pulse coupling to electron dynamics and what I call geometrically reduced systems. So these are kind of condensed matter systems, at least delocalized electron, that's the main thing. And in a setting where these delocalized electrons do not have full periodicity, that makes it interesting, hopefully, as you will see. So this work has been done, the two projects I will introduce to you in my department at the Max Planck Institute for the Physics of Complex Systems in Dresden by two postdocs, Hamed and Chuan, and of course in collaboration with my longtime collaborator and friend, who is also professor at our institute, Ulf Salman. So before I start, I give you one idea, one quick slide, what we are doing at the Max Planck Institute for the Physics of Complex Systems. That's our building. By now it's a bit older and there's more trees and so on, but still this is it. And we are a guest institution that we have many, many guests from all over the world, English-speaking institute in the midst of Germany. And we advance the theory of complex systems in condensed matter, atomic, molecular, and optical systems, and in biological physics. We are about 150, maybe now close to 200 researchers, typically from 40 countries. We have 3 directors in these 3 directions I just told you, about 12 to 15 group leaders, 40 postdocs, 30 guest scientists, and about 60 PhD students. And this is also very important, maybe interesting to you. We have about 20 international workshops per year with about 1,700 guests. And maybe most importantly, so we are really, really widespread over the world to see from the origin of the researchers. And we award essentially fellowships from 2 weeks to 2 years, very flexibly to pre-docs, postdocs, and sabbatical stays. And you can continuously apply to come to us, and the fellowships are awarded about 5 times a year by a standing committee of the Institute. So this is in a nutshell what we do. And now what our research group has been recently doing, I told you about strong field coupling to delocalized electrons. So this is the menu for today. I will give you a brief introduction about intense light matter coupling, since I figured you might not be used so much to trying to destroy your basically sample by a laser pulse. That's more or less what we do with intense light matter coupling. But this gives, of course, very interesting effects. And I will then discuss 2 phenomena, high harmonics of delocalized electrons, and there in particular the backscattering in systems with broken periodicity. And the second one is valley polarization in graphene. That has been a hot topic for a time now, and it's not easy to achieve. And I will show you that one can do this against all expectations or maybe intuition so far with ultra short linearly polarized pulses. So that's the menu, and first the introduction. And the ones of you who have been attending the previous web seminars or webinars, you might be reminded by the introduction of the talk by Manikanti Krishnamurti. I think it was webinar 8. He is also dealing with intense laser pulses, and he gave you a bit of an introduction from the perspective of the light, how these are generated. And I will give you now an introduction from the perspective of the coupling to matter or to electrons more specifically. So as a good physicist, what you should first always do, you should try to make yourself familiar with the scales involved, right? If you have a new phenomenon. And it's also for the students, I think it's really important. Physics is in general a relative thing. So you always want to compare your numbers relative to some numbers which give you the scale of the phenomenon, of the field, where this is happening, and so on. And of course, if you do experiments, also the absolute numbers are really important. I would never deny this, but as a theoretician, we always try to get rid of absolute numbers and work in scaled units. We love to do this. And of course, this also makes it happen that sometimes we have not the slightest idea at which absolute scales we work. And yeah, this creates sometimes surprises, but it's really important to work out the scales. And this is what we do now on the slide. So what are the characteristic scales of a free electron in intense field? So normally you would describe your electron dynamics by Hamiltonian. That's the kinetic energy of the electron. Let's say this is bound by some potential. In the simplest case, this would be now an atom Coulomb potential. And this is the dipole coupled light to the electron, r times the amplitude of the laser field. The laser field is written here. We use classical laser fields since they are strong. Some peak amplitude. Here it's linearly polarized in the x direction. Some time-dependent envelope, and of course the frequency of photon energy of the laser field here. Might be some phases, but that's not important. Now let's check it out. If there's no potential, what does the laser field do to this electron? So there's a characteristic length scale associated with the motion in the laser field, and this is basically the laser pushes with this oscillation here in x, the electron back and forth, right? This is called quiver amplitude, and the maximum excursion characterizes the laser field and the electron motion in it, and this is given by the peak amplitude over the frequency or energy of the photon squared. The associated momentum is then peak amplitude over frequency, and there's a characteristic energy involved in this motion, and this is the mean average energy over this full period of motion back and forth. So the kinetic energy is a squared half, right? This is just momentum, so momentum squared half would be the kinetic energy. And if you average this over a period, it gives you 1/2, so it's a squared 4. This is called the ponderomotive energy. And just to give you a feeling, if we have an intensity of the laser, peak intensity of 4.6 times 10 to the 14 watts per square centimeter, and a frequency of 800 nanometers, which corresponds to 1.55 eV, then this would amount with these quantities to 35 atomic units excursion length. So remember, this is quite a lot, since our, let's say, typical bound electron in hydrogen, this is where the atomic unit comes from, right, has a typical range of 1 atomic unit. Momentum is 4 atomic units, and the ponderomotive energy is 27 eV, just 1 Hartree. This is why I chose these numbers, but they are really fairly typical. And you see, this is also fairly high because most, valence shell electrons in elements are bound, of course, by less than a Hartree. I mean, helium is 24 eV. This is the highest binding you have. All the others are maybe 10 eV, around 10 eV or even less. So this means once you have these kind of intensity and frequency, that certainly this interaction of the laser pulse with your electron, which is bound by this potential, is non-perturbative. And what this will do is shown here. So here, schematically, here you have your Coulomb potential, and this is kind of bent down by this term, the dipole coupled term, if this is just at a phase where this is unity. And then you can see this can tunnel out here the electron. That's the binding energy. It's bound here. This is distance, x, and it can tunnel out here. We'll come to this shortly. Just maybe as a last remark on this slide, to get you a feeling what this 10 to the 14th means, if I take 1 atomic unit field strength, this means this is exactly the electric field the electron feels on its 1s kind of orbital around the ion, the proton. Then this corresponds to an intensity F0 squared of 3.5 times 10 to the 16th watts per square centimeter. You see, it is basically not yet so strong as really the electric field of the hydrogen in its ground state, but it is fairly strong. So all your perturbative photon fluxes and intensities you use for single photon ionization manipulation are way, way, way lower. Okay, so let's see. What are the main mechanisms of the strong field coupling to an electron? Of course, this is now nonlinear in the number of photons. It's nonlinear dynamics. And this is now shown here, and I alluded to this already a little bit. So you see here one effect, and that's the most important one, which triggers basically this kind of electron dynamics, is tunneling ionization. So when the field bends down, the Coulomb binding potential, then you see here the electron sitting at this binding energy, ionization potential, a vacuum level is somewhere up here, then it can tunnel through this barrier, which is not so high anymore. And this triggers basically ionization. So it's very different from the photo effect in perturbation theory. And a characteristic kind of quantity which is important here is the finite tunnel exit. You see, this is not at zero. It's at a finite distance where you exit here, this tunnel. And of course, if you look roughly at it, it's at zero because, as we said, you know, in scaled units, this distance might be a couple of atomic units divided by the scale of the quiver motion of the electron, where it can later on move, is almost zero. So therefore, often this is taken as zero. But you will see, in our context, it will become important. So tunneling ionization is one important process. Another one, which is technically even more important, is the upconversion of photon frequency or photon wavelengths to shorter wavelengths, higher energy. It's called high harmonic generation. And you see, this is a highly nonlinear process, of course, because you pack together many photons of small frequency to get one photon of high frequency. Not very efficient, so, but at least you can do this. And the way it works is the following. So once you tunnel ionize here, then the electron gets out, and eventually, at some phases, it's driven back by the laser because it's strong enough. It's pushed back to the ion. And when it comes close to the ion again, it can recombine to a bound state. And the energy which is released in this recombination process is kind of radiated off your atom. So this is now radiation with high frequency, with the frequency which corresponds to this energy difference of the continuum electron and the bound state here. And the typical spectrum looks like that. So this is the power spectrum of this radiation which is emitted upon recombination. And you see this is on a logarithmic scale. So it decays quite a bit from like the resonance frequency of the photon, the small omega, to this up conversion to high harmonics. But what's characteristic is that here's a plateau where the efficiency doesn't decrease further over quite some range of harmonic orders or energy. And then there's a sudden drop, which is called cutoff. This is essentially related to the maximum kinetic energy with which the electron can come back with a certain probability for recombination. So that's the cutoff. There are even analytical kind of approximations how to get this, but this is not of so much interest today. Why? Since we want to have basically not a localized electron, what this is, of course, a single electron, it's just local. We want to couple our light to delocalized electron in kind of a condensed matter environment. So let's look what this does. If we now think of coupling delocalized electrons to intense pulses, then of course the question is how to describe this in the first place. And of course we would like to know what happens with tunneling ionization and high harmonic generation, these two kind of archetypical nonlinear photon coupling processes of localized electrons. What happens to those processes if you come now to delocalized electrons in quasi-periodic structures? And of course, you know, in the condensed matter context for periodic structures, you would describe your dynamics in a band picture in momentum space for the electron. Now let's do this here. And what you would then do, and this is important to know now for all further considerations, so that's really important to get here. It's relatively simple to include the laser pulse into these considerations because it simply means that on your bands, which are parameterized with the crystal momentum Q or K, you simply replace your Q with the canonical momentum in the condensed matter context. This is called Bloch's acceleration theorem with Q plus A of t, where A of t is the vector potential of your laser pulse. So the field strength is the time derivative of the vector potential, right? So this is all what we need. Now let's have a look how this looks like. And maybe let's start again first with the atomic process I just described to you. So this was described in real space. You said, I showed you we have this tunneling event out here, and you have acceleration in the laser field, and eventually the electron comes back and can recombine here and release the energy in terms of this high harmonic radiation. Now, how would we describe this atomic kind of process in momentum space. This is shown here schematically. So here's the parent ion. This is essentially the binding energy, if you wish. So that's constant in Q space. That does not depend on it. It's an eigenstate. And then we have in the continuum, the ionized electron has a parabolic band, quote unquote. It's simply k squared half, right? It's just the kinetic energy. That's not really a band. It's a localized single electron, but you can describe it in this way in momentum space. And you see this band gap, what we would call band gap in the condensed matter context, is simply the ionization potential here. So we create in the condensed matter language, we create by tunneling ionization of our electron in an atom. We create an electron-hole pair. So the electron is in the continuum, moving on kinetic energy, parabolic band. And of course, what's left behind is the ion, and this we would call a hole. And essentially what happens now with A of t, we move on this band, and at some time later on, the electron can recombine with the hole. That means can recombine with the parent ion, and the high harmonic radiation is released. Now, this is, of course, now relatively easy to translate to the condensed matter context. Here, of course, we have valence and conduction bands. So let's say you have an occupied valence band here. Then you tunnel to the conduction band, of course, preferably at the smallest band gap, which is called the band gap, right? At the smallest distance here. And then you move on the conduction band, and eventually later, electron and hole can recombine. So this is very analogous to the atomic situation, and this is how we can describe or understand at least interband kind of strong field dynamics. You have also some dynamics staying in the band, but this is of no interest for what we are discussing today. We really have interband polarization or tunneling dynamics here, very analogous to the atomic case. So that's kind of the theoretical setting. And of course, the interesting question is now, this is all described in momentum space, so there is no spatial properties. But I told you that the quiver amplitude is an important scale in this process. And the question is, can this play any role, or which role does it play? And this has motivated us to kind of break the spatial periodicity, break the spatial symmetry of our infinitely extended condensed matter systems, and study a finite chain of atoms with a finite length. And this kind of introduces the effects of geometrical restrictions and has some surprising consequence, as I will show you next. So now I can come to high harmonics from delocalized electrons and this backscattering effect, which is the surprising consequence. So let's look at our system. It's very simple. You just, design a chain of atoms. Here it's schematically drawn. They have a certain kind of lattice constant, if you wish, or mutual distance. Here we take 7 atomic units. And we solve the system, by the way, with 4 electrons per atom by density function theory. And the harmonic yield, this is really the radiation we want to have, is simply given by calculating the total current time dependently and fully transforming it to the frequency domain. That gives you the radiation which we are looking for. And we normalize that, of course, per atom. We have n atoms here, so this is per n squared. And by B of k, in general, so k is now q. Sorry, before I had q for the momentum. Now in this section I called it k. My students are just using different notations. Maybe I should try to homogenize that. Anyway, so this is the band energy without specification. Of course, we will have valence bands we call V, and conduction bands shown here we call C. Now the quiver amplitude in this condensed matter system formally is given by integrating the velocity over time, right? The velocity you get by the dispersion relation. So the band energy divided by k gives you the velocity, and that integrated gives you the quiver amplitude. And you see this is not so simple. That's to be expected in the condensed matter context. So normally it would be A0 over omega squared for an atom. Here it's now, A0 over omega, F over omega squared. And here it's decorated in addition by the effective mass of our bands, since the bands have, of course, curvature, and that introduces an effective mass here. But you see that, of course, if you would have an atom, you would get directly k squared half and take the differential of that, then you get k, and that gives you the normal quiver amplitude in the atom. So that's consistent. Okay, and so what we do now is we replace our k of t, our crystal momentum, by a of t minus the starting point with the initial crystal momentum, which is normally 0. That's this replacement for the acceleration theorem, the Bloch acceleration theorem. Now let's see how this looks like. So these are the results, and we first look at the periodic case. How can we simulate the periodic case, even with this finite chain? It's very simple, and these are now introducing and really making use of the spatial scales. We take a chain length, n times d, so that's the entire length here, which is much larger than twice the quiver amplitude, specified here by the properties of the laser pulse and the band. And that means, of course, that the laser can kind of move an electron around here only very little. And so the electron will basically never experience the finiteness or the edges of the chain only here at these 2 points. But if the chain is very large, then the bulk part, so to speak, the interior of the chain, has a much larger effect than these 2 points at the edges. So that's the situation we look at here. And you see, we do this numerically once for down here for basically the periodic case. Here we really use periodic boundary conditions, so that's exactly periodic, not with this approximation. And then we take what I just said, a large basically chain length, and this is of course in relation to the quiver amplitude. Now here we have a laser pulse which has 1600 nanometer wavelength, and for that we take n equals 80, and you see this is the blue curve. And the blue harmonic spectrum agrees very much with the periodic case. So that's already asymptotic in the sense that the electrons do not feel the edges of the chain. And we can repeat this with another wavelength. Accordingly, we have now to make the length of the chain larger to be in the asymptotic region. Here it's 120. You see again, it agrees in 160, same thing. So here you see an overview where this is the harmonic order, that's the frequency of the radiation, versus system size. And you see up here you are in this asymptotic regime where essentially it's periodic, it's like the full infinite length condensed matter chain. Nothing changes here. The interesting features happen here down where the system size is relatively small in relation to the wavelengths. Of course, that's to be expected, since here we would expect these kind of finite size effects, or basically the effects of breaking the periodicity of our delocalized electrons, right? Because in these kind of cases, now the quiver amplitude is larger and actually it takes you always over the edge in most cases, if you move the electrons around in the chain by the laser. Now, before we discuss this, maybe just you get familiar with the kind of motion of our laser-driven electron in the band picture. So this is shown here again. So here's the valence band, the second valence band, which is occupied, and our electrons, which are participating in this high harmonic generation, they are tunnel ionized here at the gamma point at the band gap, and then they reach the first conduction band. And driven by this A of t, they can go out here. And you see, if they are driven here along and recombine, it gives you all the radiation, which corresponds to this energy difference, omega. And there's a limit, because here at the basically end of the bryomin zone, there's an avoided crossing, and you have to kind of come over another gap. And that reduces, of course, the yield. And this is the first cutoff here. This is omega 1, so that's the maximum kind of recombination energy or radiation frequency you can get without losing too much intensity. That's this range here in all the cases. But of course, you can go beyond this at the cost of having very much reduced intensity. You lose this here by tunneling again. And then the vector potential of the laser can drive you up on the second conduction band all the way here to this point. And this gives you the maximum energy of the second conduction band recombination, which is here. And here you would go yet to another band if it's available, again with loss of intensity. So this is the second cutoff here. So that's the situation we have in the periodic condensed matter case, and that was known before we started our investigation. Here you see what the numbers are if you're interested. So this is the field strength or the vector potential, and we use a pulse which has 4.5 cycles, and as I said, 4 electrons per atom. Now let's see if I make the chain shorter or the quiver amplitude larger. Now we take the situation, we just jump right into the middle where the music is playing, so to speak. So we make really the length of the chain comparable with the quiver amplitude, the maximum excursion, twice the quiver amplitude. And now we have a new phenomenon, which we find quite intriguing. Now we have backscattering of your electron amplitude at the edge of the chain. So now we are at this situation, system size in red, and the spectra are now the red ones. And what you see is you really get extended harmonic generation with like increased intensity up to much higher order in all cases here. And now let's try to understand where this comes from. So this is shown here. What you see is we have again our band structure, very same thing. So we tunnel ionize, we got to the conduction band, but now we have a situation where, let's say here, that's the maximum where you still have an effect of backscattering. I tell you in a second why. Here, basically, let's say you reach the end of the chain with your electron wave packet, and then it's elastically reflected at this end of the chain. That means the momentum is reversed at the scattering time, and you end up on the other side with sign of the momentum reversed, and you can move on. And this is, of course, an energy gain. And you can move now to the second band without much loss and can get here essentially this kind of radiation in terms of recombination energy. And why is this the maximum? This is the maximum simply because here's the vacuum level. So below your total potential at the edges of the chain is still bound. It can hold the electrons back. So the potential is 0, of course, at the vacuum level. Here it's bound, and therefore they can bounce back. If you are above here, then basically, if you reach the end of the chain, you are really already free, and most of the electron flux just continues and leaves the chain. So the backscattering scenario is on the conduction band where you are below the vacuum level here. This is where backscattering happens. So that's very nice. That's a new effect. It's an enhancement of high harmonic generation. One always wants that. And interestingly, this happens if you break the periodicity of your delocalized electrons. So that's really trying to relate the spatial properties of a free electron, the quiver amplitude, to something which kind of matches that in your sample, in your matter, which is illuminated. And that's here the finite size of a chain. Of course, you could think of defects or something like this later on. Now, here this is examined in a bit more detail, also overview. Now we define this critical length of the chain in terms of the quiver amplitude and the lattice constant of the atoms. And here we take a situation just to not be at the extreme, but be a bit above. And you see indeed the dynamics is really, really similar, almost self-similar, if you scale it always the right way. So the relation between the length of the chain and the wavelength or the quiver amplitude remains the same. And you see all the spectra for these three situations are very similar qualitatively. And if you plot this now against the energy, that's important because, of course, the wavelength changes. If you would take the harmonic order here, omega, this is 1 over the wavelengths. But if you plot it against the energy gained, you see essentially 3 equivalent spectra. And if you calculate the yield or the gain in terms of radiation energy below the first cutoff, which would be observed in the infinitely extended periodic situation, then you see this here, and you see there's an optimum of the chain length, and this is really very close to this kind of critical chain length where the full quiver amplitude equals the chain length at unity. So that's very nice, and that kind of establishes this backscattering effect. We can understand it. You have scaling relations, now spatial scaling relations, and that was important for us. There's one more interesting aspect, which is again maybe more for theoreticians, but I think also our experimental colleagues like that because it gives you a pictorial kind of impression what really happens. One can define electron and hole trajectories, and this is done by looking at the basically Fourier transform with the window in frequency and time of your harmonic yield, and this is shown here for the finite chain, n equals 24. And we can really define now electron hole trajectories on the conduction band, how they move. And we do this here also, of course, in space. I mean, trajectories, classical trajectories, of course, live in space and have momentum. This is unavoidable. And this gives you now a spatial impression what really happens. And you see here is the end of the chain in the one direction, in the other direction. And of course, this is exactly the reflection, this backscattering, what happens. And here's recombination. And the interesting effect is now that you need initial separation of electron and hole trajectories where they start when they are born after tunneling in order to have recombination and in order to get these black traces here. So that really describes what's in the background, the heat map that's from quantum calculations to describe the quantum yield. And these points are, if you basically ignore that and say, and this was kind of the knowledge before we started this, also in the general condensed matter context, that you ignore this initial separation, the tunneling exit distance, and take this to 0. Then you get only this. And you can now compare this for the periodic case. And also here, you see a clear improvement if you have this finite tunneling distance. And this tunneling distance is simply given by the band gap energy over the field strength at the tunneling ionization event. That's, of course, a distance. And that gives you a very good estimate. One can derive this. It's done in the paper, in the preprint here, how to do this. And you see it also improves the situation which was known in the periodic case before. So people use these kind of open circles here. It's not as evident as here. Here really don't get a lot. And this tells you again that the finite chain, of course, is more sensitive to these spatial kind of correct relations you need. But here are your electron hole trajectories for the periodic system. And you see, of course, they can do what they want. They kind of turn around here driven by the laser and not by just the end of the chain, because there is no end of the chain. They can go forever if they want, but this is just essentially driven by the quiver amplitude here. Okay, so I think this is the end of the first story, backscattering for delocalized electrons. Now let's come to Wally polarization in graphene with ultra-short linearly polarized pulses. So if I have lost you, you have another chance now to kick in because that's a new topic. And only the introduction, how to couple light, intense light to condensed matter systems will be relevant for that, because that's very similar. So just in a nutshell, what is graphene? It's hard to do this very quickly, but hopefully some of you will be familiar with that. You know, graphene is a 2D material that's a monolayer of carbon atoms, and they are arranged in this very nice honeycomb structure. And again, and the special situation is that the honeycomb structure can be thought of kind of a superposition, if you wish, of two identical translationally invariant lattices, the blue one with the blue carbon atoms and the red one, which are shifted a little bit with respect to each other. And that means that the honeycomb structure itself has basically a broken symmetry. And that leads now in momentum space. So this is really, real space where the atoms sit. And this is momentum space. And this leads now, that's the Brillouin zone here, if you wish. And this leads to 2 points, the so-called Dirac points or diabolic points, K and K prime. They are here in the band picture, where the 2 bands touch, the valence band and the conduction band. No band gap is 0. And these 2 points are degenerate in energy, that's what's shown here, but they're still not equivalent because they are a result of this interaction of these 2 different lattices. So it's impossible, I think, to grasp this as fast, but just accept that these 2 points are degenerate energy, but they are not equivalent. So that means they have 2 eigenstates, which are really orthogonal to each other, if you wish. Now we describe this with a 2-band tight binding approximation. That's a very common approximation for that system, at least close in energies to here the K points, simply because this makes such an easy transition here, and you don't have to take into consideration much higher bands because the coupling here is very, very large compared to other bands. Now, what does the Hamiltonian look like? It's very simple. It's, of course, 2x2 Hamiltonian, and we can get rid of the energy scale. So that means you have only off-diagonal terms, and that's the kind of tight binding expression for that, for those of you who are interested. And at certain Qs, now K has become Q again, momentum, you have 0. This is where you are at these points. And we solve this again by simply solving the time-dependent Schrödinger equation in the eigenbasis of this Hamiltonian. So we diagonalize it and use the eigenbasis, but that's not so important for the results in the end because they should be basis independent. And what we need to know, of course, as before, that's what I said. This is all without light. This is just crystal momentum. That's the structure of our graphene situation, giving these bands. And if you want to couple it to light, we simply make the replacement again that the crystal momentum is amended by the vector, time-dependent vector potential of our laser pulse, Q plus A of t. So we solve this for Q plus A of t, inserting here always plus A of t. So that's what we need. And now we have to look at something, or want to look at something, which is Valleytronics. And this has to do now with the fact that these 2 points, K and K prime, as I said, they are not equivalent. They have 2 orthogonal wave functions. And that means, although they are the same energy and it looks pretty much the same, we can assign a symmetry to an additional symmetry to the system, which has a different label at K and K prime. It's called the Valley index, and it's very similar to a spin, if you wish, where you also have a symmetry attached to a particle, which is not directly visible from its spatial kind of dynamics. And as the spin couples to a magnetic field, the interesting property of this Valley index, if you wish, is that it couples to an electric field. And that, of course, is very attractive if you use now strong laser fields. Another difference, which also makes it attractive, is if you think of spin, this normally requires physical charge transport. Here, the coupling to electric field does not require this physical charge transport. It only relies on interference and phase change of the wave function when exposed to the strong field. That means you could hope for a fast change of this Valley index or transport of properties from one K to another with little energy required. And of course, we are looking for quantum information realizations and so on. And this gives the hope that one might be able to store information in this Valley index. That's therefore Valley polarization and so on. But there's many, many unsolved problems. And nevertheless, the goal of all optical Valleytronics, as it's called, is to generate Valley polarization. I'll tell you in a second what this is, with a laser pulse. So what is Valley polarization? It's simply the desire to encode information in one of the valleys. That means to kind of be able to write in a controlled way, or to generate in a controlled way, a difference of the population around the K region and the K prime region. And therefore, the value polarization can be characterized by the difference of excitation probability in the part of the Brillouin zone belonging to K, this triangle, and the other one to K prime over the sum, just to normalize it. And here it's written again explicitly, so pK, ionization or excitation probability around the K point, is given by integration over all initial crystal momenta in this part of the Brillouin zone, in the red one, this triangle, and then following with this initial momentum, the final probability density in the conduction band, if this is excited or not. Maybe it stays in the valence band, then nothing happens. If it's in the conduction band, then this density gives you the measure, and integrating over that is the probability for excitation in this domain of the Brillouin zone belonging to K or K prime. So this is what we want to do. And of course, we want to kind of trigger that by a laser pulse. And you can imagine that it's not easy to get a difference or a polarization here, simply because K and K prime are energy degenerate. So more or less everything what happens to both of them, K and K prime. So how to do this? Now, so far, what people have thought, and this is even relatively new from this year, they thought of kind of designing, which is also kind of fashionable right now, relatively complicated so-called two-color clover pulses. So that's a pulse with frequency omega, which is circularly polarized in one direction, and it's superimposed with a 2 omega pulse circularly polarized in the other direction, and that traces out now this kind of figure, kind of a clover figure for the amplitude in time. If you want to follow it more analytically, it's written here, how this is expressed. And people thought this would be very good because, first of all, this Valley index is really related kind of to the sense of rotation, to kind of a chiral property. And secondly, you can see it from here. So this is the excitation kind of pattern in false colors, since this clover shape traces out the triangles very nicely. And you see directly you get kind of more ionization or excitation here in this upper triangle by this laser pulse than in the lower one. And that gives you, sure enough, so this is now, I called it kind of rho, here it's n. This is the probability in the conduction band. And you see you get indeed a higher probability for excitation in this triangle than in this one here. Yeah, that's the green one around K prime. So that's great. And these are the parameters: 6 micrometers wavelengths for the basic frequency, 10 to the 11 watts per square centimeter, relatively long pulse. Okay, but I will show you now that it's not necessary to use this complicated pulse if one really understands the mechanism of strong field excitation in graphene. So what's really sufficient is a subcycle pulse linearly polarized along the K prime direction. So linear polarized here. Here's K, here's K prime. And it should have a suitable strength and wavelengths, and then it's much more efficient. So let's look at this. This is a bit complicated, but I kind of walk you through this. But this is already the result, so you don't have to understand more. So this is our Brillouin zone again, and these are all initial conditions which lead in the end to certain excitation probabilities. So this point here, the color gives the excitation probability for the pulse we use in the end, if the initial crystal momentum was here at this point. And this is excitation probability around K is blue, and of course red, and blue is at around K prime. And now you see what happens. So we have a laser pulse which leads to a crystal momentum. It's a half cycle pulse, very short subcycle pulse. So the A is kind of starts from here, it's driven down here. And then eventually you see it goes further on and it comes back and hits kind of this point a second time and goes back to zero, of course. Yeah. And now where do you make a transition? The important thing is that in graphene, you really only have excitation probably which is kind of sizable close to a K or K prime point. That means you create two excitation bursts. One if you pass for the first time here, and another one if you pass back for the second time here. And now, depending on the phase difference here of these two excitation bursts, in the end, you get destructive or constructive interference. So you see, in this situation, you get destructive interference. So have your first point of passing of this K point, wow, it jumps up. And then you have the second one, and then you go down again because it's destructive interference. Now, if you start here with this Q value, then you get constructive interference, and you see this here, same thing, pulse, but you move up and you move the second one on the way backwards with the right phase, it gets on top, you get constructive interference and get high excitation probability. Now, if you sum all this up for different starting points here, you get this pattern, and you see already here, just by inspection, you have a preference for excitation of the red triangle versus the blue one. And here, this is now shown for different pulse intensities. And you see, and this is not so surprising maybe, what you really need is a vector potential or intensity that's related to that, of course, of your laser pulse, where the vector potential of the pulse is comparable to delta, to the distance in momentum space of k and k prime points. That's delta. And if you have this, then you kind of get the optimum valley polarization, much more excitation in the red region than in the blue one. And this gets even better if you go to like longer wavelengths. So here you see it already visually that the red part is larger than the blue part. But if you have relatively kind of short wavelengths, then the interference pattern is rougher here, and you cannot discriminate so much between red and blue. And so I won't have time to go into details here. Maybe one thing which has confused you, here we have the Brillouin zone, yeah, and here we have these squares. That's just a good representation. Since everything is periodic, you can split this here into halves and put it up here. That's really equivalent, and you see where these structures come from because they kind of continue here, but they're in the other domain. Therefore, this is colored blue and this is colored red. So this counts for excitation of K prime and this for K. Yeah, so you see it's optimal for A0 around delta here, and of course, as I said, for longer wavelengths. And we even can work out analytically a scaling of these fringes in this direction shown here, but I won't discuss this today. So to summarize again, band transitions only near K or K prime. And for subcycle linearly polarized pulse, we have these two excitation bursts here and here, which make the interference fringes. And now this is almost the end. So now since we have understood this, we can construct a pulse which should be very, very good for increasing the valley polarizations. So what we have to do is we have to avoid that kind of the wrong region here passes the excitation points. So therefore, if you are in the blue, you have very small amplitude, so nothing much happens. But once you are in the red, which you want to have, then you have large amplitude. And if you're in the red already, this wouldn't matter, but it cannot harm the same pulse. So it gives the same excitation. And you see our original pulse, just a single half cycle pulse, is this dashed line, and that also excites here in the blue range. And this pre-pulse, so this is with a pedestal, small, and then on top, the half cycle pulse, this is much better and really reaches relatively large valley polarization. That's the last slide that's shown here. That's a summary, basically. Here's the valley polarization achieved. So you see here in dashed, that's the original kind of clover pulse I showed you, which reaches, yeah, some valley polarization. Also, again, maximum around when the strength of the pulse is around delta. But you see this kind of pedestal pulse, very short, but with a long pedestal, reaches much higher valley polarization. And it's also better to have longer wavelengths, which is green here. So the original 800 nanometers is not so good. That's what I showed you. And also what's very important is you do not want to destroy your sample, right? Or heat it up a lot. This is always a problem with intense pulses. And you see that our pedestal pulse is doing very well here. So this is the excitation probability, the total one that stays relatively low. So you have large valley polarization with at the same time low total excitation probability, which unfortunately is not the case for the clover pulse. The clover pulse is actually very good to have a high overall excitation, but not so much for valley polarization. So that brings me almost to the end. So that's what I already said. We can get high valley polarization and low excitation damage for linearly polarized half-cycle pulses, in particular with the pedestal. And as a summary in general, to come back to the scheme or this, of breaking the symmetry, you probably should think of intense fields like forming together with matter an entire total system. So laser plus pulse plus matter forms the system. And that means you can think now of periodicity breaking of the system within the first Brillouin zone, also through the laser pulse, not just by manipulating the matter, because the laser pulse is an integral part of your system. This is kind of the feature of intense field physics. Okay, so that's a summary. I think I let this stay here and probably already over time. So let me thank you for your attention. And I'm, guess, ready for questions.